Already.
Hello everyone, my name is Farman and I am from BBRD College. So today I am going to show about my PMSM motor which I have designed for the Alteflex Competition 2025. So PMSM stands for Permanent Magnet Synchronous Motor and I have given an output rated of 7 kilowatts which is approximate of 6930.628 watts. Like supply voltage I have used for 72 volts DC which is commonly used by all EV vehicles, and its connection is three-phase connection, and rated speed is about 5000 to 5100 rpm, and current is 5.5 amperes, and rated torque is 50 newton meter, and number of poles is 12, like 6 poles per pair, and speed of operation is maximum bit set to 5100 rpm, and materials used like I have been using standard materials in Altair Flux motor. Based on my configuration, I have been using the standard materials in the available materials in the Altair Flux motor, and power rating is about 7 kilowatts. And these are the some advanced specification like stator design, outer diameter, stator slots, material use, lamination, PMSM, and rotor. This is about rotor design, which I have specified diameter, poles, magnet thickness, materials, designs, and air gap I have kept off to 0.25 mm to reduce the sine wave losses, like here current losses, and to get a better sine wave. Materials like material properties, cooling system like oiling and natural cooling system. I have been using winding configuration and multi-layered winding, which is three-phase simulation test and optimization. So let's go into the motor design. So this is the interface of the motor which I have been designed, and it is a data sheet, axial view, and this is a view, like overview. um, I have been using Harpin winding technology for the more advanced winding for my motor to get the best output. Like rotor diameter, I have been using uh, outer rotor diameter outer rotor diameter instead of air gap and stator inner diameters. So I have been configured outer diameter as 190 millimeters. Inner diameter is 150.6, like approximately 156, and number of slots are 72, and number of poles are 12, based on the slots. So next, let's go to the housing. Like housing, I have been using housing instead of square one. Like I preferred using circular circular housing for my motor, like fin type. And for outer cooling, I am using radial fin type for better cooling. And I have been circuit in the user like rectangular circuit selection. Like I have based on my research, I have seen that circular rectangular circuit selection is more efficient than circular one. So this is the data sheet, and this is the design configurations, and like design configuration we can able to see here. And let's come to shaft design and bearing. Design and bearing, like design I have been constructed like design, like this is the parameters I have given for my uh, shaft and bearing. And I have been using a bearing here, like we know for the bearing is used for better friction and many more. And this is the configuration like I have set it for my uh, shaft. Magnet, let's come to the magnet. I have taken off magnet shape of like simply IMD block D. IMI block D. I have selected this one, which was best for my motor. Like, and I have set my magnetic motor thickness, space between them, magnet outer arc, Q axis arc, and bridge and axis. And outputs I have got this as expected. Like polarization. Like I have been given a polarization of 90 degrees angle. Like one motor one magnet is having its own polarization. One is clockwise, anti-clockwise, like inside outwards, inwards outwards, like our example, like our drone motors. So local, and this is the skew, and for this I have done skewing, and for this I have done skewing, and I have left is skewing for slot. Like as we cannot do both skewing for the both slot and magnet. um, This is a magnet, this is the skewing part, and this is the data sheet. I will provide it. Local data sheet, and this is the design configuration of my motor. As you can see, for skewing mode, I have been using custom. I wanted to use linear, but for the advanced and better results, I have been using custom one. So I have set it up and set up values like angles. These are the angles which were set up by me. Uh, and then let's go to the slot section. Like slot, it is designing the slot shape. I have been using the free A slot. We can also use the free D slot, but I have been selected free A slot, and it's where the inputs I have given, and lamination. And I have been using the circular as my housing is as my housing is design is circular. I have been using this circular lamination and skewed. And skew part is skipped here because we are not able to skew both magnet and slot skewing at a time. And winding. This is the main part. Like I have been using an advanced winding here, like uh, advanced winding for my PMSM to achieve the best output. Uh, so number of layers are 2, number of conductor of layer per 2, layer shift is 1, and number of color parts are 2, and coil. Based upon coil, I have been using like four coils, 4 coils in a part. Like inner spacing, I have adjusted here, and insulation part, I have done insulation for each and every one to prevent short circuits. And end winding, I have been using this end winding extensions in meters. I have been also adjusted this one. Then comes to cooling. Like it is a data sheet I have been provided here. You can able to see data sheet. Um, and This is a view of my motor. And this is the convection. I have been using force convection. It is as we know, force convection is better than natural convection mode. So I have been using force convection for better output and efficiency. And I have been using machine orientation as horizontal, like basically, and fan tip ratio to 3.2 and altitude of 0 meters. And cooling circuit, this one I have been adjusted. And radiation, I have framed to infinite. It was around 1, so I have adjusted to 0.9 for emissivity. Then X factor, I have been designed for calibrations and model evaluations, and my machine maximum speed is 5100 RPM as my design, based upon my design. And cooling, internal cooling. So here also I have been using force cooling part. Uh, ba- uh, Force cooling part instead of natural one. And radiation I have been using frame inner surface rotor and stator. And interface, I have been using this interface, and I have adjusted these nearby to the values. And slot, and I have been I thought to use this auto slot, but user slot, and I want to adjust the radial and orthogonal and axial slot, so I have been using this user slot. And then X factor. These X factors were approximately near to 1. So I also set it as this values to nearby 0.9, 0.9. All this OCS and CS and internal opposite connection sites and opposite connection sites and magnetic circuit and maximum speed, as I have already said that my motor maximum speed is 5100 rpm, and internal fluid temperature is around 35. Based on test I have been using nearly 20 degrees. So materials, so main points. So here base based on my machine, I have been using here the best magnets. Like it was the best here, like difference ND Nido EM FBB 1370, which was the best of all these magnets. And circuits, M3030, M330 35 amps 35A, and copper coil. And insulation. And for internal fluid, I have been using natural cooling air. For cooling circuit, I have been using water for the uh, better cooling purpose, like external fluid like insulating oil. So let's come to the test part. Like I have been testing this all parts. Here mechanic parts are disabled because I have been used queuing in my test. And these are the performance like OCC test, like open circuit test. Here I have got these values, and I have given the input parameters. Back EMF test, I have got these values, graphs, and graphs, and I have achieved an efficiency motor based on my one. This is the current motor graph generator. Like this is the character motor characterization. These are the graph I have been achieved. Uh, and next, I have been using this data sheet like overview. These are the values I have been using. And thermal, based on thermal, I have set it to winding shade part temperature to 60 degrees, connection side to 65, opposite connection side to 65, and magnet temperature about 50 degrees. So this electronic parts, power electronic stage, I have been using instead of circle maximum linear range of triangle. So I can attain a good power electronics and DC bus bar voltage to 550 watts and maximum efficiency 99% and rated voltage is 7 kilowatts as I have discussed. Um, then next mechanics part. I have given the reference speed as like my speed is 5100, losses as reference speed is 150 and speed exponent 1.8. And I have set this input values and this advanced values also I have been set it and I have run the test and saved the test like thermal. I have got this thermal and I think I have reached a good thermal point and these were my results. Like and I have done transient testing. Transient testing like these were my results for the transient testing. Uh, like fitting. Fitting also I have done based on, I have been using various parameters for my test to obtain the best result. I have been using testing it several times. So I have got this test. I have deleted the previous one. Like this is the graph, X factors, parameters, temperatures we can see and working point. Based on the SAR instructed, we have to use only sine wave for the PMSM. I have been using both sine wave and square wave. Like this is my result for the sine wave, and I have got a graphs in it, and this is the current current control angle speed. Same thermal points I have kept for it. Like electronics, same power electronics and mechanics, same. I have been using these parameters. And then torque versus speed. Speed we have got these results, and these are the curves I have been got like. And these are the flux density versus mechanical angle graph, and this is the current voltage graph I have got, and these are the table values. Uh, I think I have been achieved good points like torque, BRF, refill torque, working point, refill torque, power electronics, winding, inputs, settings. I have been using, and this is the generator part. Like inputs I have given, settings, its winding is this, working point, B graph. I have got for this generator one. This is the resistance inductance speed. Like this is the inputs. These are the inputs I give, and these are the settings, winding magnets, OCC, and working point. And it is a B graph. B graph, flux density versus air mechanical angle graph. And I have also tested for several times, and I have kept the final results, like best results. So this is the square wave. I have test. This is the synthesis. This is the back EMF, torque graph, phase voltage, line voltage, phase current, line current, power, losses. I have got, and these were the inputs which have been set. And the same thermal, like same thermal and same mechanics. And advanced mesh coefficient I have been using like 8.1.0 or 1.5, and now for this I have kept for 1.0. And next is performance mapping. Here I have kept the maximum RMS voltage of 420 volts, and I have been severally testing for number of JD and JQ for 8, number of components of speed up to 20, and number of torque up to 10, and air gap mesh coefficient up to 1.0 and 1.5. For 1.5 I have got the results, and this is for generator overview. Generator overview, these are the results which I have been obtained like current, torque, voltage, control angle, power factor, and losses. So as I have seen, my graphs were accurate. And for motor, mainly these were the inputs, settings, winding magnets, base speed, maximum speed table, torque, current, voltage graph, current angle, power factor, losses, and we can see these were the linear, and I think I have got the best one like linear graph, efficiency, current graph, voltage graph, current control angle graph, power factor, losses, uh, losses, and lastly mechanics. This mechanics is disabled because I have been using skewing for my motor. At last, I have exported my report, as I want to export it to Flux 2D, but it is not possible because I have done skewing in it. At last, I want to thank Alter Flux for giving me this opportunity, and to my staff, to my faculty members for giving me this opportunity. So by this, I have been uh, came to a base idea like how to design a motor, what is queuing, what is like what are the poles, number of poles, test, what is OCC, and in basic college level type we can see only OCC like BA, back EMF and fogging. But here I have learned what is modal, what is data sheet, what is thermal, like sine wave. First time I have been seen we can use also use square wave in our motors, like performance mapping and mechanics. Lastly, like flux theory and more. So, um this is this is my motor, and thank you.